While Toyota, Samsung, and Western giants quietly test their scaled-down battery technologies, Huawei has just played a wild card that sent shockwaves through the entire auto industry. A solid-state battery, potentially capable of delivering a jaw-dropping 1,968 miles, or 3,000 kilometers range for electric vehicles. This is no longer a competition between individual models or brands. This is a survival race. If other automakers don't catch up with this technology within the next 2 to 3 years, they risk losing the market altogether. We're talking about batteries with twice the energy density of today's 4680 cells, a 4-minute charging capability, and a battery architecture that tackles the biggest flaw of solid-state tech: rapid degradation. And perhaps the most chilling part? Tesla is going all in on this front with a cold ambition, pushing past 1.3 million vehicles per year at its Shanghai Gigafactory. After all, Huawei is just one name among over 7,600 battery patents filed annually in China. And in the end, it's no longer about who leads on paper. It's about who can turn lab promises into mass production reality. The answer may well shape the entire future of transportation in the decade ahead, and you need to know about it now. Welcome to Tesla Car World. How does a 1,968-mile battery truly lead the pack? Is it for real, or are they just blowing smoke? Let's be real, nobody saw this coming from Huawei. We mean, this is the phone company we all know, the one always in the headlines for clashing with Western governments. They're not a car maker, and they've never been a big name in EV batteries either. But out of nowhere, they drop a bombshell. A brand new solid-state battery with energy density hitting 500 watt-hour per kilogram. To put that into perspective, that's nearly double what you'd find in a current Tesla long-range model. And it's not just about cramming in more energy. Huawei claims they've tackled the biggest issue that's held solid-state batteries back for years: the rapid breakdown at the interface between lithium and the solid electrolyte. Basically, most solid-state batteries degrade fast, especially at the point where the magic happens. But Huawei says they've fixed that by doping sulfide electrolytes with nitrogen. Sounds super technical, but the short version is, it works. If true, this could be the missing puzzle piece the whole industry has been looking for. Now, about that 3,000 kilometers range, or around 1,968 miles. Yeah, sounds kind of wild, right? Like, why would I need to drive from Los Angeles to Chicago without stopping? But that's not the point. The real value here is flexibility. Automakers could use this tech to either build smaller, lighter, more efficient EVs, or just keep the same battery size and give drivers 1,000 to 1,500 miles of real-world range. Either way, that's bad news for gas engines, because suddenly EVs wouldn't just be cleaner. They'd be better in almost every way. Lighter, faster, longer range, cheaper to fuel. Game-changing stuff. Let's talk about charging for a second. One of the biggest gripes people still have with EVs is charging time. What if I forget to plug in overnight? What if I'm in a hurry? Well, that excuse is about to expire. Companies like Zeekr, BYD, and XPeng are already testing batteries that can charge in just 5 minutes. Enough to give you around 300 miles of range. And no, this isn't just happening in China. Ultra-fast charging stations are being installed across Europe, the US, and even Australia. Before long, charging an EV will be like grabbing a cup of coffee. You pull over, take 5, and you're good for the next few hundred miles. Now let's not get ahead of ourselves. This tech still costs a pretty penny, up to $1,200 per kilowatt hour. That's about 20 times more than your typical LFP battery found in affordable EVs today. So yeah, early models using this battery will be high-end. Think luxury cars, supercars, or cutting-edge electric SUVs. But remember how OLED TVs used to cost an arm and a leg? Now you can grab one at Walmart during Black Friday. Solid-state batteries will likely follow that same curve. Premium today, mainstream tomorrow. So, is Huawei leading the pack, or are they just making a lot of noise? Honestly, it's too early to say. They've filed patents and made bold claims, but there's no car in any dealership you can actually buy yet that uses this tech. Still, one thing's clear. Chinese tech giants aren't playing around. They've got the cash, the talent, and the motivation to shake up the EV world for real. Meanwhile, over in Japan, Toyota promised back in 2021 that they'd have a solid-state EV ready soon. Well, it's 2025 now, and guess what? Still no sign of one hitting the lot. At this rate, it's starting to feel like waiting for Half-Life 3. Everyone says it's coming, but no one knows when. So yeah, Huawei jumping into the battery game might seem random at first, but when you look closer, it might be the start of a major shift. Not led by the traditional car makers, but by tech companies with massive R&D budgets and a point to prove. And when companies like that get serious, well, the rest of the world better pay attention. So between solid and semi-solid battery. Why Huawei's 1,968-mile battery could leapfrog 24M's tech. In the fast-evolving world of electric vehicle technology, two disruptive battery technologies have emerged from opposite sides of the globe. On one hand, we have 24M Technologies, a US-based startup that stunned the battery world with its Eternalite electrolyte, enabling rapid charging, outstanding cold weather endurance, and world-class safety features, all without resorting to solid state. On the other, we find a surprising new player in the EV battery game, Huawei, the Chinese tech titan better known for telecommunications than transportation. Yet Huawei's recent announcement, a solid-state battery with an energy density of 500 watt-hour per kilogram, enough to power a car for up to 1,968 miles, may prove to be the more disruptive of the two. While both technologies represent remarkable engineering, Huawei's foray into solid-state power reveals deeper, potentially more transformative implications for the industry. It's not simply about high numbers, it's about redefining the physics and scalability of battery design in a way that could render today's EV limitations obsolete. Let's start with the raw numbers. 24M's Eternalite system, combined with their novel Impervio separator, reportedly achieves 660 watt-hour per kilogram, the highest energy density ever confirmed in a non-solid-state battery. This enables theoretical ranges of up to 1,000 miles, 1,600 kilometers, and fast charging times as short as 4 minutes for 300 kilometers. Huawei's technology, on paper, falls slightly behind in energy density, 500 watt-hour per kilogram. However, that's a misleading comparison if viewed in isolation. Huawei's battery is fully solid-state, meaning the form factor allows for greater safety, packaging efficiency, and system integration. Solid-state batteries eliminate the need for bulky cooling systems and complex thermal controls, which means more of the car's weight and volume can be devoted to usable energy. Thus, while the per-kilogram energy metric favors 24M, the real-world system-level energy density, taking into account packaging, thermal management, and fire safety, very likely tilts the balance toward Huawei. Moreover, Huawei's innovation isn't just a speculative claim. They've filed a critical patent that outlines how they've overcome the long-standing Achilles heel of solid-state batteries: the rapid degradation at the interface between lithium metal and the solid electrolyte. By doping sulfide-based electrolytes with nitrogen, they reportedly stabilize the material interface and dramatically reduce the electrochemical decay that has long prevented solid-state batteries from achieving commercial viability. In doing so, Huawei appears to have crossed a scientific threshold that countless battery researchers have been chasing for over a decade. 24 million batteries enable impressive range, up to 1,000 miles. But the implications of Huawei's technology stretch even further. The 1,968-mile range potential completely reshapes what is physically possible in EV design. This is not merely a question of efficiency. With such a leap in usable energy per charge, automakers gain flexibility. They can build compact EVs with half the battery size, reducing weight, cost, and resource consumption. Or They can maintain current battery sizes and deliver ultra-long-range vehicles that eliminate range anxiety for good. They can optimize battery placement and design architectures that were previously impractical due to heat, weight, or cooling constraints. No less important is the potential lifespan and degradation profile. While 24M's electrolyte dramatically improves lithium battery performance, especially in cold weather, it's still bound by the inherent constraints of liquid electrolytes, including issues like gradual capacity loss and dendrite formation over long charge cycles. In contrast, Huawei's solid-state approach minimizes dendrite risk, operates without flammable liquids, and can theoretically maintain capacity for thousands of cycles with far less degradation. 24 megabytes currently leads in charging speed metrics. The ability to deliver a 4-minute charge for 200 miles, 300 kilometers, without requiring ultra-high voltage infrastructure is a major practical benefit, especially in countries lacking dense EV charging grids. Their Eternalite technology also sidesteps the need for 1-megawatt chargers, allowing 24M-equipped EVs to thrive even on standard 400 or 800-volt systems. Huawei has not yet released real-world data on charging speed, and it's possible that initial versions of their solid-state battery won't match 24M's blistering charge times. However, this doesn't mean Huawei lags behind. Solid-state chemistry naturally lends itself to higher charging potential as thermal issues are minimized and voltage tolerances are higher. Once infrastructure and power electronics catch up, Huawei's batteries could charge at faster speeds without the need for elaborate liquid cooling systems. Moreover, the need for ultra-fast charging is arguably reduced by Huawei's energy reserve. If a car can drive 1,500 to 2,000 kilometers on a single charge, users may only need to recharge once every week or two, changing how we think about EV ownership entirely. Safety is a critical concern in battery design, and here both companies deserve credit. 24M's Impervio separator offers state-of-the-art protection by suppressing dendrites and enabling early detection of internal shorts. Their battery platform maintains 80% capacity even at minus 40 degrees Celsius, a milestone unmatched by current lithium-ion solutions. This makes 24M's technology ideal for cold weather regions and contributes to the claim that their electrolyte might be the most robust non-solid-state platform ever built. Huawei's solid-state system, however, eliminates the core fire risks altogether. By using a non-flammable solid electrolyte, they bypass the possibility of thermal runaway, the primary cause of EV fires and recalls. While Impervio is a remarkable safety innovation for liquid batteries, solid-state remains inherently safer, offering a fundamentally fireproof architecture that regulators and automakers alike will increasingly demand. 24M's greatest strength is its scalability. Eternalite and Impervio can be licensed and integrated into existing lithium-based battery production lines with minimal retooling. This lowers the barrier to adoption and offers an immediate pathway to market. Huawei's approach, by contrast, is longer-term and more disruptive. Their battery is likely still in early prototype or lab-scale testing. Manufacturing solid-state batteries at scale remains a challenge, and cost per kilowatt-hour is currently estimated at 20 times that of LFP batteries. But as we've seen with screens, lithium-ion cells, and other technologies, costs drop rapidly once manufacturing matures. The big picture here is that Huawei is not simply building a better battery. They are building a new battery paradigm. By investing heavily in material science, interface stability, and solid-state architecture, Huawei is setting the stage for the post-lithium era. 24M's battery is, by many metrics, the best liquid-based battery system the world has ever seen. It is fast, cold-resistant, efficient, and safe, an ideal solution for the immediate future. But Huawei's battery hints at something bigger, a step beyond the boundaries of what we thought possible. With nearly 2,000 miles of range, non-flammable chemistry, and the potential for new vehicle design philosophies, Huawei may not just be improving EV batteries, They may be redefining what a battery-powered vehicle is. How will these batteries impact Tesla affordability? Such a breakthrough aligns perfectly with mass-market vehicles. Take Tesla's rumored $25,000 Model 2 EV Gen 3. A solid-state battery like Huawei's would reduce cost, meet strict tax credit criteria, and unlock exceptional range, making it globally competitive even before subsidies. A 3,000 kilometers range would make the Model 2 a disruptive force in regions with poor charging infrastructure, especially Southeast Asia, Africa, and Latin America. Even if initial deployment is limited to premium models, the long-term strategy is clear. Replace lithium-based cells in entry-level EVs to meet cost and policy targets. This gives both Tesla and emerging automakers a blueprint for scaling sustainable, locally compliant vehicles without relying on vulnerable lithium supply chains. Additionally, Huawei's battery could revolutionize stationary energy storage. With zero risk of thermal explosion, ultra-long cycle life, and efficient performance in cold climates, these cells could power everything from remote data centers to decentralized renewable grids, especially in places like Tibet, Scandinavia, or Alaska, where lithium storage suffers. The ability to discharge down to 0 volts without damage enhances flexibility for off-grid use. From a manufacturing standpoint, Huawei's battery maintains partial compatibility with lithium-ion production lines. Retooling costs are estimated at only 10% over existing Li-ion factories, making the transition economically viable. This is key for gigafactory owners reluctant to overhaul infrastructure. The core science behind the battery centers on solid electrolytes and advanced nanostructured electrodes. Unlike conventional graphite anodes, Huawei's model may use engineered ceramic or sulfide-based electrolytes paired with high-capacity metallic lithium or silicon anodes. These offer high ionic conductivity, thermal stability, and better interface contact, all key to delivering both fast charging and longevity. Globally, this puts pressure on companies like Toyota, Samsung SDI, and QuantumScape, who have been researching solid-state batteries for years without commercial rollout. Huawei's unexpected leap forces these players to accelerate. Even Tesla, though silent, is rumored to be working on parallel architectures and has already registered several relevant patents. Should we trust a tech company like Huawei to lead the EV battery revolution, or should car makers stick to what they know? Tech giants versus automakers. Who wins this race? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. The most critical component of an electric vehicle is the battery, but if it fails, you might have to replace the entire floor of the car. This isn't just a design weakness, it's a ticking time bomb for the future of EV. Now imagine a battery lighter than ever before. One thin enough to cut a laptop's weight in half, slim enough to make phones as thin as a credit card, and powerful enough to boost an EV's range by up to 70%. And here's the kicker. It doesn't swell while charging, doesn't grow dendrites that cause short circuits, doesn't deform on impact, and doesn't degrade quickly over time. Why is that? Welcome to Tesla Car World. So, what is this strange breakthrough battery? First, we're going to take a quick look at the structure of this special type of battery, before we dive into how it could be used to build phones as thin as a credit card, or whether it could really boost the range of an EV like the Tesla Model 2 by 70%. That's coming up in 2 minutes 46 seconds of today's episode. The one at Korea Advanced Institute of Science and Technology, KAIST, which has developed a high-density structural battery made from a multifunctional carbon fiber composite. Their innovation lies not only in materials selection, carbon fiber for strength, and solid polymer electrolyte for ion conductivity, but also in the process of integrating those materials. Resin, a core component of the composite, typically traps air during curing, weakening both structural and electrochemical performance. To address this, KAIST employed vacuum compression molding, which tightly controls temperature and pressure during fabrication. The result? A cleaner, pure, minimal trapped air, and a composite that delivers both robust mechanical properties and battery-like functionality. Their achievement is notable: a 160% increase in carbon fiber volume. Fraction compared to previous efforts, yielding a structure that is lighter, stronger, and capable of storing energy. This isn't a proof of concept on paper. It's a manufacturable design using well-understood industrial processes, meaning it could, in theory, be scaled. Meanwhile, across the globe at Chalmers University of Technology in Sweden, researchers led by Leif Asp have been making quiet, steady progress with a different structural battery composite. Their design also uses carbon fiber composites, but with a twist. The carbon fibers serve dual purposes as both the structural support and the electrodes. A structural electrolyte completes the system, enabling ion flow through a material that's as stiff and lightweight as many metals. According to early projections from the Chalmers team, structural batteries could cut a laptop's weight in half, reduce a smartphone's thickness to that of a credit card, or boost an EV's range by up to 70%. These are bold predictions, perhaps even optimistic, but they illustrate the transformative potential. Think of it like baking a classic pie, a flaky crust on the outside, a sweet or savory filling on the inside. Now imagine trying to make that pie tastier, lighter, and more nutritious. You'd naturally wonder, why should the crust exist only to keep everything in place? Why can't it be both sturdy and as nourishing as the filling itself? Yes. By replacing both the chassis and the separate lithium-ion pack with a carbon fiber laminate that stores energy while carrying load, an average mid-size electric vehicle could drive roughly 70% farther on a single charge. Computer models show that today's 450 kilograms metal bodywork and 500 kilograms of standard cells can give way to a 30 watt-hours per kilogram structural pack weighing about 750 kilograms. Yet the car still loses around 200 kilograms overall because the old chassis disappears altogether. Lower mass, coupled with the extra space freed inside the floor, translates directly into longer real-world range. The same material promises equally striking gains at smaller scales. Prototype laptop housings built from the laminate deliver the stiffness of aluminum, about 70 GPa, while storing enough energy to eliminate the separate battery modules. Because the shell now doubles as the power source, Chalmers engineers calculate that a typical notebook's total mass could fall by roughly half without losing runtime. For smartphones, the team has demonstrated single-sheet cells only 0.8 millimeters thick that function as the device's mid-frame. Tech Radar reported that this could enable handsets less than 4 millimeters deep, essentially the thickness of a credit card. Between the first 2021 prototype and the latest 2024 version, gravimetric energy density rose from 24 watt-hours per kilogram to 30 watt-hours per kilogram, while mechanical stiffness nearly tripled. Safety has advanced as well. The new architecture uses a semi-solid electrolyte and cobalt-free chemistry, so it neither swells during fast charging nor forms the metallic dendrites that trigger shorts in conventional cells. So why are EV makers betting on eliminating lithium in EV? When most people think about electric vehicles, they focus on things like range, charging time, and battery capacity. But what if the next big breakthrough in EVs wasn't about putting in a better battery, but rather about turning the entire car into a battery itself? That's the strange and exciting idea behind structural batteries, an innovation that could transform how we design vehicles from the ground up. Instead of simply improving the chemistry of batteries, structural batteries flip the concept entirely. These are materials that serve both as structural components, like the body or frame of a car, and as energy storage. In other words, rather than having a battery inside the car is the battery. This may sound futuristic, but companies like Tesla and BYD are already moving in that direction. Tesla has begun integrating battery packs as structural parts of its Model Y and Cybertruck, reducing the number of separate components and improving vehicle stiffness and efficiency. Meanwhile, research institutions and manufacturers around the world are racing to develop structural battery materials that are strong, lightweight, and capable of storing real amounts of energy. So why are some of the most forward-thinking EV companies betting on structural batteries? The answer is a combination of performance, efficiency, and design flexibility. Today, EVs carry their battery packs in heavy, rigid containers placed low in the chassis. That adds weight and eats up valuable space. But with structural batteries, you get to eliminate the traditional chassis and the traditional battery enclosure, because they become the same thing. You might replace a 450 kilograms metal frame and a 500 kilograms battery pack with a single structural component that does both jobs and weighs significantly less overall. The benefits go far beyond saving weight. Reducing mass makes EVs more efficient. Every kilogram saved means less energy needed to drive the same distance. Some computer models show that a well-designed structural battery could allow a mid-size EV to travel up to 70% farther on a single charge simply by cutting dead weight. Not only does this reduce the cost per mile, but it also opens up design possibilities that were previously off-limits due to bulky batteries and heavy structural components. This is why automakers are so intrigued. If they can fuse two of the heaviest parts of a vehicle, the battery and the frame, into one, they don't just save weight. They free up internal space, improve driving dynamics, and potentially lower costs in the long term. Some of the most promising progress has come from researchers working with carbon fiber composites. These materials are already known for being lightweight and incredibly strong, used in everything from sports cars to aircraft. But now, engineers are figuring out how to make carbon fiber composites store electricity. By embedding them with conductive materials and solid-state electrolytes, researchers have developed a carbon fiber-based structural battery with a significant boost in energy density and strength, thanks to clever resin chemistry and vacuum molding techniques. Their approach packs more carbon fiber into a tighter space while avoiding the air bubbles that weaken both structure and battery performance. In Sweden, researchers at Chalmers University have created a structural battery that uses carbon fiber not just for strength, but as both the electrodes and current collectors in the battery. Their latest version reached an energy density of 30 watt-hours per kilogram. That's still a fraction of traditional lithium-ion batteries, but it's a major leap from earlier prototypes. According to their estimates, such batteries could eventually cut a laptop's weight in half, allow smartphones as thin as a credit card, or even significantly increase the range of an EV. Of course, this is not to say that structural batteries are ready to replace traditional batteries across the board. They still have significant hurdles. The biggest challenge is energy density. Structural batteries simply can't store as much energy per kilogram as today's high-end lithium packs. For now, they are less suited for applications where maximum range and compact size are non-negotiable. But in many other use cases, particularly where space and weight savings are just as important as battery life, structural batteries show immense promise. Aircraft designers, for example, are deeply interested in them. Planes are extremely weight-sensitive, and every pound saved extends range or increases payload capacity. Some research groups are already building lightweight structural supercapacitors into fuselages and wings, demonstrating that these ideas aren't just theoretical. Another major factor driving this innovation is sustainability. Structural batteries are expected to use fewer raw materials by replacing multiple components with a single multifunctional one. This could lead to simplified manufacturing, fewer emissions during production, and better recyclability, especially as composite materials and solid electrolytes improve. Unlike many other next-gen battery technologies still stuck in the lab, structural batteries are already being integrated into real products, at least in limited ways. Tesla's battery-integrated chassis is arguably the first step toward this future, and it shows how structural energy storage can already help reduce complexity in production and improve vehicle performance. Still, this technology is far from mature. For full structural battery adoption, manufacturers will need to solve issues related to safety, such as swelling and deformation during charging, and long-term durability. In traditional batteries, these issues are isolated. But if your car's frame is also your power source, any physical damage becomes a much bigger problem. There's also the economic factor. Right now, structural batteries are expensive and difficult to mass produce. Capacity, materials, vacuum, forming, and precise layering don't come cheap. Like with many new technologies, structural batteries won't reach cost competitiveness until they can scale up, and scaling up requires big investment, strong partnerships, and a fair amount of risk-taking. Yet, despite these obstacles, the industry's interest is growing, and the more real-world applications we see, the faster the pace of innovation. With structural batteries, companies aren't just asking, how can we make a better battery? They're asking, why does a battery need to be a separate thing at all? That's the kind of thinking that drives real disruption. So why are EV companies betting against traditional lithium battery design? Because structural batteries offer an opportunity to break free from the compromises we've lived with for decades. Instead of being limited by where the battery fits, how heavy it is, or how hot it runs, structural batteries offer a way to build the battery into the bones of the vehicle itself. That's a powerful idea. Lithium-ion batteries aren't going anywhere soon. They're still the best option for most consumer electronics and long-range EVs. But the shift to structural batteries suggests that a new layer of innovation is unfolding. One that changes not just how batteries work, but what they are. The next generation of EVs might not carry their batteries. They might be built from them. How are structural batteries being tested on EVs? Those longevity claims may sound fantastical, yet they track with numbers already measured in accelerated aging chambers. A recent peer-reviewed trial at the Materials Performance Institute cycled a 400-plus 400mm structural panel more than 3,500 times at 95% depth of discharge while subjecting it to alternating tensile loads that mimic pothole strikes. At the end of the test, capacity had fallen by only 15%, a figure usually reached by standard nickel-manganese-cobalt packs after just 1,000 deep cycles and almost no mechanical abuse. That performance stems from two intertwined breakthrough decus: a semi-solid polymer electrolyte that heals micro-cracks as they form, and a nano-textured carbon fiber weave that spreads strain so evenly the active layers behave more like a rubber sheet than a brittle ceramic. The payoffs extend far beyond raw durability. In a mid-size crossover, think of something between a Tesla Model Y and a Toyota RAV4, the conventional chassis panels weigh about 420 kilograms, while a separate 82 kilowatt-hour battery pack adds another 510 kilograms. Structural powertrain engineers aim to replace both assemblies with an integrated 100 kilowatt-hour tub weighing 650 kilograms. Although that looks heavier at first glance, the deletion of stamped steel, cast aluminum, and multi-part crash rails leaves the overall vehicle 180 kilograms lighter. Computer simulations run at Oak Ridge National Laboratory predict that every 100 kilograms of mass trimmed from a modern EV extends real-world driving range by about 6%. Combine weight savings with a 22% gain in volumetric energy density, made possible because you no longer waste space on hangers, brackets, or air gaps. And the same crossover is projected to travel 75% farther than its bolt-on battery counterpart while drawing from the same public fast-charging network. To push those range gains even higher, researchers are changing the chemistry that lives inside the carbon shell. Instead of the traditional cobalt-heavy blends popularized over the last decade, several groups are experimenting with high-nickel, low-cobalt spinel cathodes stabilized by aluminum doping. These materials offer 260 watt-hours per kilogram at the cell level, only 10% shy of the best pouch cells shipping today, yet they tolerate far greater compressive stress because the three-dimensional spinel lattice resists the volume swings that typically fracture cathode layers. On the anode side, the go-to recipe mixes silicon nanotubes with a thin surface grafting of lithium phosphorus oxynitride, a coating that locks silicon in place during expansion so it cannot pulverize or form conductive dead ends. When that anode is impregnated directly into the carbon fiber filaments, electron pathways shorten by more than half, Cutting internal resistance to a level where 5 to 80% charging in 12 minutes becomes plausible at 350 kilowatt roadside stations. Cold weather resilience, the Achilles heel of nearly every electric powertrain sold today, benefits just as dramatically. Standard graphite electrodes slow to a crawl below freezing because the electrolyte thickens and the intercalation process grows sluggish. The polymer electrolyte in structural batteries, by contrast, transitions into a slightly rubbery state at -15 degrees Celsius, yet retains ion mobility on par with liquid carbonate solutions at room temperature. During a recent winter trial in Duluth, Minnesota, a prototype structural battery sedan lost only 9% of its nominal range when ambient temperatures hovered between -10 degrees Celsius and -20 degrees Celsius, compared with a 28% drop recorded by a conventional pack running the same route. Safety concerns, particularly the fear of catastrophic fires, have guided every design decision. Because the electrolyte is semi-solid, it will not leak, pool, or vaporize even if the enclosure is punctured. Moreover, the carbon fiber frame acts as a Faraday cage, dispersing heat and electrical arcs so quickly that local hotspots seldom exceed 120 degrees Celsius, well below the runaway threshold. Engineers blast-tested sections with aluminum shrapnel at 200 meters per second. The worst damage was a shallow crater that never breached the innermost current collector layer. If your EV's chassis and battery could be combined into one ultralight, super-strong structure, would you feel more confident about driving it, or more nervous knowing the entire car is the battery? Why? Please share your opinion in the comment section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. It's great to see US companies finally taking action to push the battery industry to the next level. We all know the truth. Batteries have long been the weakest link in the electric vehicle world. Not the design, not the range, but the cost of manufacturing and replacing them. Ask any car salesperson, and they'll likely dodge the question. Why? Because no one has managed to bring battery replacement costs down to a level consumers can afford. But now, the 24-megawatt semi-solid-state battery claims to do just that, thanks to its simplified design with semi-solid-state cells, fewer components, and sandwich-style assembly. The result? Lower fire risk, easier recycling, a remarkably low cost of just 6 cents per watt-hour, and the ability to fully charge in just 4 minutes. But the lab is easy to talk about. Mass production is the real test. Charge-discharge cycles must be validated with real-world data, and few manufacturers are willing to openly discuss battery degradation. But if 24 million can prove its durability, US electric vehicles may finally break free from dependence on Asian battery suppliers, and budget-friendly models like the 11,800 BYD Seagull or the 24,400 XPeng G6 long range will never be a threat to the American EV market. Could this finally be the tipping point for the US to lead in battery manufacturing? Welcome to Tesla Car World. Today we're taking a closer look at the semi-solid-state lithium-ion battery technology developed by 24M. 24M, short for 24 Molecules, is a battery technology firm headquartered in Cambridge, Massachusetts, USA. They've distinguished themselves with a unique semi-solid platform engineered to tackle the 4 biggest challenges in the battery industry: driving down costs, boosting safety, increasing energy density, and maximizing recyclability. So how does 24M's semi-solid battery turn the 6 cents per watt-hour price into reality? This $0.06 per watt-hour claim is universally regarded as an extremely dubious assertion, lacking rigorous scientific evidence, a solid verifiable foundation, or validation. Any basic market observer with even minimal awareness also knows that current lithium-ion battery pack prices sit at approximately $115 per kilowatt-hour, means $0.115 per watt-hour. So a $0.06 per watt-hour headline rate implies a massive 48% discount over the already optimized current costs, a proposition that remains entirely questionable, implausible, and unfeasible with today's global battery manufacturing technology at scale. Even leading battery scientists and seasoned market research experts in their most optimistic and cited projections only anticipate that average global battery pack prices will gradually decline to below $100 per kilowatt-hour by the year 2025. So where does $0.06 per watt-hour figure come from? And why is 24 million's battery able to accomplish this feat? Remember back at Battery Day, 2020. Elon Musk and Tesla consistently pursued dramatic cost reduction and significantly enhanced battery performance, publicly targeting an ambitious $60 per kilowatt-hour goal at Battery Day 2020. And just 5 years later, that ambitious goal has fully materialized in published data, and we believe this extremely low price point derives from large-scale research experiments, because realistically it would be nearly impossible to achieve at an internal or pilot production scale. Imagine a battery factory as a construction site where, instead of laying 20 painstaking rows of tiny bricks, brick, mortar, workers now install a few massive precast panels that raise the full height of the wall in a single lift. That is essentially what 24M's semi-solid process does. It cuts the number of individual placements in half, wiping away hours of labor and slashing the energy bills that normally keep the lights, ovens, and precision robots humming. Because each panel is poured as one dense slab, it ends up twice as thick as a traditional brick layer, so the same concrete footing supports far more material. Pay for the foundation once, carry double the load, and the cost per square foot, or per watt-hour, plummets. The advantage compounds inside the car itself. Where a typical electric SUV hides hundreds of brick-sized cells under the floor, 24M replaces that clutter with half a dozen wall-sized sheets, the company's so-called carpet cells. Fewer parts mean fewer welds, wires, screws, and cooling plates, which quietly chip 10 to 15% off the final bill while also removing dozens of potential failure points. The streamlined approach even reshapes the factory. With less real estate and equipment to finance, the company can build a plant for roughly half the cost, then pass the savings straight to automakers. This battery can run iron-based LFP powders, high nickel blends, or even future sodium chemistries without ripping out its tooling. That agility shields pack prices from wild swings in metal markets, and it shows up where it matters most. A 75 kilowatt-hour battery that costs about $8,600 today could fall to roughly $4,500. Couple that drop with a $7,500 federal credit, and a mid-size electric crossover can undercut a gasoline SUV right on the showroom floor. Because the panels are cast in Massachusetts, the pack also clears new rules that penalize Chinese components, so more models stay eligible for incentives. Best of all, the same design that makes the battery cheap lets it add 200 miles of range in 4 minutes and keep working in -40-degree winters. So, how can they prove that a 4-minute charging time isn't just hype? It's an undeniable fact that even the most advanced semi-solid state batteries on the market today can only charge from 15% to 90% in up to 18 minutes. Likewise, CATL's publicly announced fastest charging technology delivers 320 miles in just 5 minutes, but it doesn't achieve a full 100% charge in one session. And, as everyone knows, Tesla's cutting-edge superchargers still require 15 minutes to add 200 miles. You might not believe it, yet take a look. CATL has just unveiled its second-generation Shenzhou battery, capable of providing 323 miles, 520 kilometers of range in only 5 minutes of charging. That extra minute's difference shows that a 4-minute boost is not only feasible, but entirely within reach. If there's one thing that still holds people back from switching to electric vehicles, it's not the range, it's the charging time. But what if you could charge 200 miles of range in just 4 minutes? And you don't need a custom-built megawatt charging station. Unlike traditional lithium-ion batteries or even solid-state designs, these batteries use a proprietary electrolyte known as eternalite. While the company is understandably secretive about the details, after all, revealing too much could mean handing the keys to competitors. What's publicly known is already jaw-dropping. Eternalite has 3 times the ionic conductivity of standard electrolytes. That means ions, the tiny charge carriers that flow between the anode and cathode, can move way faster, resulting in dramatically shorter charging times. According to internal testing, 24M cells can add 200 miles of range in under 4 minutes, and they don't require exotic hardware to do it. Unlike other fast-charging batteries that rely on 1 megawatt ultra-high-power chargers, which are expensive, rare, and often require special infrastructure, 24M's battery charges just fine on standard 400-volt and 800-volt platforms. That means no major overhauls to the grid, no custom cooling systems, just plug in and go. That alone is revolutionary. But it gets even better. Thanks to the eternalite electrolyte, 24M's batteries perform incredibly well in cold environments, one of the Achilles heels of most lithium batteries. Standard lithium-ion cells lose 25 to 30% of their capacity at 0 degrees Celsius and perform terribly at minus 20 degrees Celsius. But eternalite keeps on going. In testing at minus 40 degrees Celsius, 24M cells maintained over 80% of their capacity and full energy transfer. That's virtually unheard of, and it makes these batteries perfect for cold weather markets like Canada, Northern Europe, or even military operations. Think about how we refuel gasoline cars. A typical gas stop takes about 5 minutes. Until now, EVs just couldn't compete with that. You had to plan your routes around charger availability and wait times. But with this tech, the EV charging experience becomes just as fast and convenient as gas, maybe even faster. More exciting, this performance doesn't come at the expense of cost or safety. In fact, the fast charging capability is a direct result of the chemistry, not brute force. Eternalite enables high current flow without overheating, and it pairs with 24M's proprietary impervio separator to prevent the risk of thermal runaway. This means faster charging without the fire hazard that often plagues high-speed charging designs. By eliminating the traditional bottlenecks of charging time and cold weather performance, 24M is knocking down 2 of the biggest walls blocking widespread EV adoption. And the fact that this can be done without exotic infrastructure means the path to mass deployment is wide open. So, why can it kill China's LFP technology? We must acknowledge that China currently controls more than 80% of global LFP battery production. At the same time, LFP batteries accounted for 82.8% of all battery installations in China in April 2025, and CATL and BYD remain the industry giants, holding 38% and 17.2% of the worldwide market, respectively. Besides, we've probably heard all the buzz around solid-state batteries, how they're the next big thing, promising higher energy density, better safety, and longer lifespan. But they also come with sky-high costs, slow manufacturing ramp-ups, and persistent issues with degradation. Rather than go down the solid-state route, 24M has developed something entirely different: semi-solid lithium-ion batteries. This simplified process opens the door to thicker electrodes, meaning higher energy density and longer range per charge. In lab testing, 24M's batteries have achieved a stunning 660 watt-hour per kilogram, far beyond the 400 watt-hour per kilogram mark that's considered transformative for aerospace, high-performance EVs, and electric vertical takeoff and landing aircraft. But great design isn't just about performance, it's about solving real-world pain points, and 24M does that with recyclability and safety in mind, too. Let's talk about recycling, one of the biggest bottlenecks in the battery industry. Most lithium-ion batteries today require harsh chemical processes to recover usable materials, costly, inefficient, and environmentally damaging. But, thanks to 24M's Life Forever architecture, there's a smarter way. Because the electrodes are free from binders and formed in thick cast layers, they can be mechanically separated at end of life, No fire, no acid baths, no black mass. This allows for up to 98% material recovery, all through a clean and scalable process. It's a true step toward a closed-loop battery economy, easier thermal management. It's simpler, safer, and reduces system costs by an estimated 30% per kilowatt-hour. Even better, it scales. Manufacturing is already semi-automated and production-ready, paving the way for rapid adoption. And it's made in America, ready to challenge not just the limits of what's possible, but also the global supply chain that's long held the EV industry hostage. What do Elon Musk and Tesla say about this semi-solid-state battery? With all the standout advantages discussed, ranging from higher energy density and improved safety to scalable, cost-effective manufacturing. It's no surprise that semi-solid-state batteries are starting to attract attention from major players in the EV industry. But what about Tesla and Elon Musk, the names synonymous with cutting-edge innovation? What do they have to say about semi-solid-state batteries? And more importantly, have they started using them? Surprisingly, Elon Musk has never publicly endorsed semi-solid-state batteries the way he's hyped solid-state batteries in the past. In Tesla's Battery Day presentations and recent investor briefings, the focus remains on the company's 4680 battery cells, a next-gen version of traditional lithium-ion technology. There's been no official mention of semi-solid-state batteries as part of Tesla's core development strategy. However, just because Elon isn't talking about it doesn't mean Tesla isn't paying attention. As with many disruptive technologies, Tesla tends to test and experiment behind the scenes, and only goes public once a solution is close to commercial viability. Some industry rumors suggest Tesla may have explored partnerships with US-based semi-solid battery startups, but ultimately walked away due to material cost concerns at the time. It's worth noting that Musk's philosophy has always focused on scalable practicality, meaning a technology not only has to work, but it must be mass-producible at a reasonable cost. Solid-state batteries, for all their promise, still struggle in that department. Semi-solid batteries, on the other hand, are inching closer to meeting those real-world requirements. At this point, Tesla has not yet deployed semi-solid-state batteries in any commercial vehicles, but key Tesla suppliers, particularly Panasonic and CATL, are actively investing in hybrid battery technologies, including semi-solid variants. This suggests that Tesla is keeping the door open, especially as competitors like NIO and Toyota have already announced plans to pilot semi-solid batteries in long-range electric vehicles. Elon Musk once famously said, "Solid-state batteries sound great, but they're insanely hard to manufacture at scale. That's why we're focused on tech we can build now." While he wasn't referring directly to semi-solid batteries, his words inadvertently support the semi-solid approach, which bridges the gap between current-gen lithium-ion and fully solid-state designs. It's safer, more flexible, and far more viable for mass adoption. Some industry analysts believe that in the coming years, as Tesla maxes out the potential of the 4680 and the pressure to improve weight, range, and energy density intensifies, they'll be forced to revisit semi-solid-state batteries as a logical next step. So, while Tesla hasn't made a move yet, one thing's clear: Elon Musk is watching. And with the current pace of innovation, it wouldn't be surprising if Tesla suddenly announced a future Model 3 or next-gen roadster powered by semi-solid batteries, built on a quiet partnership already in the works. It's an inevitable choice, if not a leading-edge trend in technology, because in just a few years, when the Earth's average temperature climbs close to 113 degrees Fahrenheit, you'll realize just how vital electric vehicles really are. It's no coincidence that governments around the world are actively promoting EV adoption and offering generous incentives like the $7,500 federal tax credit in the US, a prime example. It's a smart policy, but it brings with it a significant challenge: the looming scarcity of critical materials used in lithium batteries. Supply simply won't keep up. Do you think Tesla will eventually ditch solid-state dreams and pivot to semi-solid-state batteries, especially if they're cheaper, safer, and faster to charge? Why hasn't Elon Musk jumped on this yet? Please share your opinion in the comment section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. Goodbye.